So in this video, I introduced the method of integration by parts. So one of the problems we have with integration is that there's no such thing as a product rule or a quotient rule. But the derivative rule for products can be, in a way, undone. Just assume that u and v are both differentiable functions of x. Then by the product rule, the derivative of the product is the first factor times the derivative of the second plus the second factor times the derivative of the first. If you then just integrate that in terms of x all the way through, and keeping in mind that since I'm still using integration, there's an unknown constant that I have not yet included in the answer. That's okay. Notice that you have a dv over dx times dx and a du over dx times dx. You can abbreviate them to get this instead. Finally, if you just go and solve for the integration of u times the differential dv, it's the same as u times v minus the integration of v times du. This is called the method of parts. So notice that the u has to be some function of x, and the dv stands for some kind of differential of a function. So it's actually the derivative of some function times dx. Now, this integration of parts is just a means to an end. It's very similar to substitution. It just converts a current integrand into a new one. So before I go and do a few examples, let's talk about how and when to use integration by parts. So pretty much you want to try this method after you've tried substitution a few times, but before you've tried any of my more advanced rewriting techniques, like before trying completing the square, before you try multiplying the numerator and denominator with some kind of function. You might even want to consider doing this before you try using trig identities. Also remember that the u times dv is just the product f of x dx. So keep in mind that whatever you pick for u and whatever you pick for dv, that product has got to be f of x dx. Also, if you need to make a decision, often you want to focus on u. What should u be? Because you need to take its derivative. So you want to pick something that once you take the derivative, it tends to become simpler. So usually we pick u to be a logarithm or one of the inverse trig functions or a polynomial, because all those things, if you take their derivatives, they tend to become simpler. Or a trig function or exponential, because at least in those cases, if you take a derivative of a trig function or exponential, many times they don't become more complicated. They still essentially in their family of functions. But whatever you pick for u, keep an eye on what dv then has to be, because you have to integrate that thing. So let's go ahead and try it once. Let's find the antiderivative of 4x times e to the 3x. Here I would definitely try parts, mainly because I have a polynomial times something. So usually I'll just try u then is equal to 4x, and then dv has to be the rest of that particular integration, which here would be e to 3x dx. So du then is just the derivative of 4x, which is 4, times dx, and v is then the antiderivative of e to the 3x times dx, and that would then be a 1/3 e to 3x. So by parts, this integral, after I use these particular choices for u and dv, it has to be u times v, so that's a 4x times a 1/3 e to 3x. You then subtract the integration of v times du. So that is a 1/3 e to 3x, and your du, which is a 4 dx. I'll just go back now and clean that particular integration up. That then becomes 4 times a third, that's 4/3. I have an x and an e to 3x. I subtract, then I have the antiderivative of 4/3 e to 3x dx. I then find that antiderivative however I can. In this case, you could just use substitution, but it's a rule by now you probably have seen enough times that the way you go about doing it is you have the 4/3. You notice that the antiderivative of e to the x should be e to the x. So the antiderivative of e to the 3x should be e to 3x, except this derivative of this particular function, being 3, would have to be present in here in the integrand. But it isn't. So I'm missing that multiplication of 3. So it must have canceled with a third. I just multiply by the constant that was missing, or at least the reciprocal of the constant that was missing. And then I add my constant of integration. So my answer then is 4/3 x times e to the 3x minus 4/9 times e to the 3x plus c. And that's the answer to the problem. If you want to make it look nice, you could. You could, for example, take 4/9 and factor it out. You could take an e to 3x and factor it out. What would be left over then would be a 3x minus 1. And in that case, if you wish to do so, you really should write it as 4/9. Put the polynomial first and then the exponential. But either's right. It's just that most people prefer that second method. That's the answer to that problem. So let's try integration by parts with this particular integral. So once again, I'll try that u will equal to x squared. That means then that my dv would have to be everything else, which would be e to the negative x over 5 dx. This time I'll go straight up and down. So this will be my du would be 2x dx, and my v would then be equal to let's see, the integration of that would then be a negative 5 e to the negative x over 5. And now that I have that, this will then correspond to, if I use this particular integration by parts on this integral, that'd be u times v, so that's x squared, times v, which is negative 5 e to the negative x over 5. I then subtract the integral of v times du, which would then be a negative 5 e to the negative x over 5. And then my du, which I'll put that in parentheses, make it a little easier to read maybe. Really shouldn't do that, but it's okay. I'll then come back and clean this up a little bit. This is then negative 5 x squared e to the negative x over 5. Then I have a 2, I have a 5, I have a negative that makes plus 10, the antiderivative of a x e to the negative x over 5 dx. Notice I didn't take the 10 out, because why bother? I'm going to need to do this integral anyway. I can take care of the constant however I wish. I choose to leave the 10, the constant, inside. It just winds up being a little easier usually to do so. Well, if you look at that particular problem, though, you now notice that I have another integral where it's a polynomial times an expression. Well, I should try parts again. This time, though, I'll have that u is equal to 10x, and dv would then be e to the negative x divided by 5 dx. That would then mean that du would then be 10 dx, and v would be, that's still the negative 5 e to the negative x over 5. So this would then become, I have negative 5x squared e to the negative x over 5. I then have plus, and I replace all of this with parts. So by the method of parts, I have u times v. That would be a 10x negative 5 e to the negative x over 5 minus the integral of v, which is a negative 5 e to the negative x over 5, times my du, which here is just 10 dx. I won't put that in parentheses this time. Now I'll clean that up. That is then the same as writing negative 5x squared e to the negative x over 5. I'd have a minus of 50x e to the negative x over 5. And then I have a plus times a minus, that's a minus. But then I have a minus 5, that's a plus integration of 5e to the negative x over 5 dx. Oh, and I have a 10 back here, so that'd be 50 then. 5 times 10 would be 50. And that's my new integral. Notice the whole thing, when I just keep using parts, the only thing parts accomplishes is to turn the old integral into a new one. You still have to do the new integral by some other technique. You're not going to be able to stop. So here, though, we notice that that's negative 5x squared e to the negative x over 5 minus 50x e to the negative x over 5. And then you have plus, well, you'd have a 50. The antiderivative of e to something, when it's just off by constant, is e to the negative x over 5. But the derivative of this exponent is negative 1/5. There was no negative 1/5 here. So it must have canceled with a division of the same thing. So I will multiply by the reciprocal of the constants missing. I'm missing a negative 1/5. So I'll divide by that. I'll multiply by that reciprocal. That would then be negative 5 plus c. This then is negative 5x squared e to the negative x over 5 minus 50x e to the negative x over 5. You'd have minus 250 e to the negative x over 5 plus c. And that is the answer. Of course, we probably wouldn't leave it that way. If you do this, I wouldn't mark it wrong, but probably wouldn't leave it this way. I probably would take out a negative 5. I would also factor out an e to the negative x over 5. And what would be left over then is an x squared plus a 10x and then plus 50. Because it just makes the answer look nicer. And then you have your constant of integration plus c. That's the answer to that problem. So let's try it again. Let's find the antiderivative of this particular function, in this case in terms of theta. So since I have a polynomial times something, I'll hope by parts that if u was theta and dv was the secant of theta tangent of theta d theta, then du would just be d theta. Don't forget you have to take the differential of this function, while v would be the antiderivative of this differential. And the antiderivative of the secant of theta tangent theta, that's just the secant of theta. So using this as I use parts on this integral, that would then be u times v. Then I have minus the integration of v times du. That would just be the secant of theta d theta. Before I continue, I'll make that look a little nicer. That would then be just theta, the secant of theta, minus the antiderivative of the secant of theta d theta. And we recall that the antiderivative of the secant of theta is, you then have the minus because of the minus before that integration, natural log absolute value of the secant of theta plus the tangent of theta plus c. That's the antiderivative for that particular function. Let's go ahead and try to use integration by parts in order to find this particular indefinite integral. Well, thing is though is that u is not always a polynomial. Even if you see a polynomial as a product in the integrand, it's not always it. You should try u as the logarithm first, try u as one of the inverse trig functions next, then you would try algebra polynomials, then you try trig functions and exponentials. In this case, I'd actually try that u would equal to the natural log of x, and dv would then be x squared dx. Notice the product of these two is still all of that. So I'd have du would then equal 1 over x dx, and my v would then be the antiderivative of x squared, which is 1/3 x cubed. So this integral will then be u, the natural log of x, times v, 1/3 x cubed, minus the integration of v, which is 1/3 x cubed, times du, which is the 1 over x dx. So I'll just clean this up. First, rewrite all these products. That would then be 1/3 x cubed, natural log of x. You then have minus the antiderivative of a 1/3. And x squared times 1 over x, that's just x squared. That's x cubed times 1 over x, that's just x squared dx. And that final integration is very easy to do because we all know that you just go and take the exponent, increase it by 1, and then we multiply by the reciprocal. So we multiply a third by a third to get to 1/9. And our integration constant. That's the antiderivative by parts. This one's a particular favorite of mine because people look at it and go, well, there isn't a product though. There's no product. So then how can you use integration by parts? Because it's a u times a dv. Where's the product to use it? Well, there is a product. It's just the arctangent of x times a dx. So here I would try that u would be the arctangent of x, and dv would just be dx. That would then mean then du would equal 1 over 1 plus x squared dx by just taking the derivative of the arctangent of x, and v would just be x, being the antiderivative of 1 dx. So our integration, after these particular substitutions, well, not substitutions, but using parts, that would then be u, which is our arc tangent of x, times our v, which is x, minus the integration of v, which is x, times our du, which is 1 over a 1 plus x squared dx. And as I've shown you every other time, I'm just going to make this look nice first. This is the same as writing x times the arc tangent of x minus the antiderivative of an x over 1 plus x squared dx. And that's our new integration we need to do. You'll notice, though, that this particular integral, if you take the derivative of the denominator, it is 2 times the numerator. So this can be done by using substitution. And in fact, it winds up being the log rule. It's the natural log absolute value of 1 plus x squared. The derivative of the inside is 2x. I'm missing a 2. So I'll multiply by the reciprocal of the coefficient that was missing. And I'll add on my constant integration. Now that last integral, sometimes people can't see it. So if you need to, you just take your work, separate it, and do the extra integral off to the side using whatever technique you need. So in this case, doing it slowly, this is the same as writing if u is 1 plus x squared, then my du would be 2x dx, which means x dx would then be 1/2 du. So this integral becomes the integration of, I get a u in the denominator, and the x dx becomes a 1/2 du. That clearly is 1/2 the antiderivative of 1 over u du, and that is 1/2 the natural log absolute value of u plus c. And just by returning what u is equal to, you get 1/2 natural log absolute value of 1 plus x squared plus c. And we're right back to where we were before. Just if you do these little side works, integrations, don't include the integration constant yet. Don't have to do that until the very, very end. And that's the answer to that problem. So you've seen the worth of using integration by parts as a means to find the antiderivative of certain products. But I derived that formula, integration by parts, by looking at the derivative of the product u times v. There are plenty of examples where you want to, when you do a integration by parts, it results in yet another integral, which is still a product, and you just won't use integration by parts again. But you wind up using u and dv in the new integral being essentially the same kind of choices you made the first time. In that case, you use what's called repeated parts. Now, it winds up being that it falls into a kind of pattern that it's actually easier to just recognize the pattern and use that instead of being a slave to using u and dv multiple times throughout the entire problem. Let me show you what I mean. Let's find the derivative of u times v prime. So then that's just me writing down the product rule. Notice if I take the antiderivative of this all the way through in terms of x and then just solve for a certain integral, you wind up getting that. That's just doing parts. I can do the same thing on, if you look at the derivative of u prime times v, just reversing the order. This time I would get that particular sum of products. And once again, integrating on both sides in terms of x and solving for a particular integral, you wind up getting this. This is once again just using parts. It's just this time we have derivatives involved. But if you look at the particular integrals, you might notice that they kind of chain together. So if I started with the integration of a function of u times a function of v's second derivative in terms of x, you could use the first integral equation I gave you to get this result. But then the integral we're left with is found in the second equation. So I know how to replace it. So I do. And then I can distribute the negative to get this particular result. That is using integration by parts twice. Well, we'd love to be able to do this and to do it quickly. So because of that, there's a nice way to represent the work by using a table. The first column is repeating signs, plus, minus, forever. And it just starts with a plus. The second column starts with u, and then you just write down successive derivatives of u beneath it. The third column starts with the second derivative of v, And then you just take successive antiderivatives. It's just as far as you need. Notice that if you look at the very first row and multiply them together, do you see how you get the integrand for the first integral? If you take the very last row and multiply those together, notice you get the integrand of the integral you get left with at the end. And if you're wondering where the other terms come from, if you take these products, start with the plus, go to the right and multiply, and then go down to the right to get to v prime. Multiply those together, and do the same starting at the minus sign. Start with the minus sign, go to the right, get to u prime, go bottom right, that would be v, multiply those together, and notice you get that particular sum. So that table, that's called the tabular method. It's just using repeated parts over and over and over again. In this case, just doing parts twice. It's just a way to organize the work and make it be a little easier to follow. Now, don't feel like that you have to do it only twice. You can continue the chart if you want. You can go a whole nother line. The next row would then be minus the third derivative of u, and then you need the antiderivative of v. But you can keep going as long as you can do the derivatives of u's, and as long as you keep doing the antiderivatives of those v's. You're good to go. Let's go ahead and use it at least once. So I'm going to use integration by parts here. But if I were to do that, I would pick u to be x cubed and dv to be e to the 2x dx. I would notice that when I take the derivative of x cubed, I would get 3x squared. It's a polynomial. And the antiderivative of e to the 2x would have e to the 2x in it. So then the new integral would still be essentially the same form as this integral, except the power on x would go down by 1. So I would just use the integration by parts again on that, where the u would then be 3x squared. Instead of doing that, I'll use the tabular method. That way I can do repeated parts quickly. So I have plus or minus. I have plus, then my u, which would be my x cubed, then my dv, which is e to the 2x. This will be our u, this will be our dv, and we'll just ignore the dx in our work. The next row is a minus, then I take a derivative, 3x squared, then I take an antiderivative of e to the 2x, which is 1/2 e to the 2x. Then I have a plus, I take a derivative, that'd be 6x. I take an antiderivative, that'd be 1/4 e to the 2x. Then I have a minus, I take a derivative, that'd be 6. I take an antiderivative, that's 1/8 e to the 2x. I can stop if I want. If you want to keep going, you can. As long as you keep doing work, as long as you keep having derivatives and antiderivatives, you can keep going as long as you like. I'll stop here though. This will then be equal to, you multiply these together, and then that one. That is a 1/2 x cubed e to the 2x. Multiply these two together, and then diagonally down to the right, that's this one. So that's a minus 3/4 x squared e to 2x. Then multiply these together, and diagonally down to the right, that's this one. So that's plus a 6/8, that's a 3/4 x e to 2x. And if you just go and multiply all the way across the bottom, that's the final integral to do. So it's minus the integration of 6/8, which is, well, 3/4 e to 2x, and then finally our dx. So that's using repeated parts over and over and over again. The last integral obviously is very easy. So the answer is 1/2 x cubed e to 2x. You have minus 3/4 x squared e to 2x plus 3/4 x e to 2x. And then you have minus 3/8 e to the 2x plus c. That's the answer. Now, of course, if you don't want to leave it that way, you don't have to. You can pull out a common factor here at least, or a couple, in order to make it look nicer. So you could write the answer as 1/8 times x cubed minus 6x squared plus a 6x minus 3 times e to the 2x plus c. It's a little nicer to deal with it that way, but they're both correct. I just prefer the second one because it's simpler to deal with. And that's the answer to that particular problem. Let's go ahead and try parts one more time. To find the indefinite integral of this particular function, I'll definitely try parts, but there's no obvious choice because normally I make u be something so that when you take its derivative, it becomes simpler. Here, that won't happen. The derivative of e to the 2x will just have e to the 2x in it. And the derivative of the sine of 3x, well, that's not going to become any simpler either. So instead, I'll just go ahead and dive in and just use parts and see what happens. But for reasons you'll see in a minute, I am going to choose to use repeated parts, and specifically by the tabular method. Why? Because it works really well. Let me show you why. This case, making a little table. I'll have a plus and I'll have a minus. I'll have plus to start off with. I'll have my u, which will be, let's say, doesn't really matter what we pick, but I'll pick the sine of 3x because I'd rather take derivatives of trig functions than antiderivatives. And then my dv would then be e to 2x. The next row would then be a minus. I need the derivative, which would then be 3 cosine of 3x. I need the antiderivative of e to the 2x, which is 1/2 e to the 2x. And then just doing it one more time, I get a plus. I need the derivative, which would then be a minus 9 sine of 3x. And then one more antiderivative back here would be 1/4 e to 2x. Now what I want you to do is look at the very first row and multiply it all the way through. See how you get the first integral? If you multiply all this all the way through, notice don't we get the same functions? That's bad, right? We don't want that. We want things to change in some way, and yet it didn't appear to. It did. It did. It just have to be careful. Notice, just write it out. This will then be multiply these two together, then multiply that together. That is 1/2 e to the 2x, the sine of 3x. Then multiply these two together, and then that one. That would be a minus 1/3. Well, no, sorry, 3/4, minus 3/4 of e to the 2x times the cosine of 3x. And then just multiplying across the last entries here in the row would give us a minus a integration of 9/4 e to 2x, the sine of 3x dx. So unfortunately, that's what we get. So in order to find the antiderivative, we need to know the antiderivative. That's disaster. But that's okay. That's okay. There's ways to get around that particular problem. The reason is that this function is continuous. If it's continuous, then we know from Calc 1 that it has an antiderivative. So this thing exists. There is a family of functions whose derivative is going to be e to the 2x, the sine of 3x. So we know then that represents something. Well, there happens to be on the right-hand side, just going to write it once, it's 1/2 e to 2x, the sine of 3x, minus 3/4 e to 2x, the cosine of 3x. Take the constant out. You have minus 9/4, the integral of e to 2x, sine of 3x dx. This is the thing we want to know. There it is also. It's an algebra problem. I'm going to add 9/4 of this integral on both sides. So I'd have the integral of e to 2x sine of 3x dx, and I'll add to it 9/4 of the exact same integral, e to 2x, the sine of 3x dx, and that still equals what we had before. That's the 1/2 e to the 2x sine of 3x minus 3/4 e to the 2x cosine of 3x. But on the right-hand side, I have 1 of this integral and 9/4 of that integral. I can add those together. That would then be, 13/4. It's 13/4 of that integral that I'm trying to find the value of. That then is equal to 1/2 e to the 2x, the sine of 3x minus 3/4 e to 2x, the cosine of 3x. Now just multiply all the way through by 4/13 to get the final answer. The antiderivative of e to 2x, the sine of 3x dx, would then be, take 1/2, multiply it by 4/13. That would then be 2 13ths e to 2x, the sine of 3x. Then you have minus. Take 3/4 and multiply it by 4/13. That'd be 3/13 e to 2x, the cosine of 3x. That's the antiderivative. Now that I finally found it, I can add on the constant integration. And that's the answer to the problem. This is the typical way to solve this problem. Don't really do anything else. This is by far the simplest way to handle it. Anytime you have an exponential times either sine or cosine, try this thing. You'll notice that when you do parts twice, the integrand you had in the beginning will be very similar to the integrand you have at the end, except there'll be this constant right here that is not +1. It'll be something else. You then just add the correct amount of integral on both sides and solve for the integral you need to know. Let's try one last indefinite integral. To find this particular antiderivative, I'm going to use parts again. Most people would try u is equal to x cubed and dv is equal to the square root of 1 plus 4x squared dx. But right away you should notice that this antiderivative, you don't know that off the top of your head. So while this is something you could try, it's not going to work. So let's try something else. The trick is to notice that the integrand here with the dx just has to be u times dv. So the u could be anything, the dv could be anything. You just want to pick a choice so that you can take its derivative and dv you can integrate it so that when you're done, the final integral hopefully is simpler. Our problem is that we don't have a nice way to take the antiderivative of a square root of 1 plus 4x squared. But we would if we just rewrote this integral once this way. Write it as x squared times x times 1 plus 4x squared to the 1/2 power dx instead. Then I would use u would then be x squared and dv would then be x times 1 plus 4x squared to the 1/2 power dx. Because that would then mean my du would then be 2x dx and my v would be then the antiderivative that you see here. You would then have a 1 plus 4x squared. We would increase the power by 1 to get 3/2. You'd have to compensate by multiplying by the reciprocal of that power. That's 2/3. Notice though the derivative of the inside is 8x. I don't have an 8 here. So I'll compensate by multiplying by the reciprocal of the constant I don't have. So that would then be 1/12 times 1 plus 4x squared to the 3/2 power. Now that I've done that with this use of parts, I can now write down the integral is going to equal, it'd be u times v. So that winds up being 1/12 x squared times 1 plus 4x squared to the 3/2 power minus the integration of v times du. So I have a 2 times the 1/12, that's a 1/6. There's an x, and there is a 1 plus 4x squared to the 3/2 power dx. That's it. That's using parts. And then if you want, you can do it again. Notice though that the derivative of the inside here, that derivative is 8x. I have an x, but I don't have an 8. So I can write the answer down quickly just using mental substitution. I get 1/12 x squared, 1 plus 4x squared to the 3/2 power. I have a minus of 1/6 because of the constant. I'd have a 1 plus 4x squared. I'd increase the power by 1 to get 5/2. I'd multiply by the reciprocal of that power, that's 2/5. And then the derivative of the inside was 8x. I don't have the 8, so I'll divide by the 8 that was missing. And then add my constant. That's the answer. You just have to clean it up to make it look nice. And that gives you a fairly quick introduction to integration by parts.